Next, we are going to talk about deep learning for graphs and in particular graph neural networks. So now that we have kind of refreshed our notion of how general neural networks, deep neural networks work, let's now go and generalize neural networks so that they can be applicable to graphs. That's what we are going to do next. So the content is that we are going to talk about local network neighborhoods. And we are then going to describe aggregation strategies and define what is called computation graphs. And then we are going to talk about how do we stack multiple layers of these neural networks to talk about how do we describe the model, parameters, training, how do we fit the model, and and give a simple example for unsupervised and supervised training. So this is what we are going to talk about and what we are going to learn in this part of the lecture. So the setup is as follows. We are going to assume we have a graph G that has a set of vertices, a set of nodes. It has an adjacency matrix. Right now, let's assume it's binary, so means unweighted graph. Let's also, for simplicity, assume it's undirected, but everything will generalize to directed graphs as well. And let's assume that every node also has a node feature vector X associated with it, right? So what are node features? For example, in social networks, this could be user profile, user image, user age. In biological network, it could be a gene expression profile, gene functional information. And for example, if there is no node feature information in the data set, what people like to do is either use indicator vectors, so one hot encodings of nodes, or just a vector of all constants value 1. Those are two popular choices. Sometimes people also use a degree a node degree as a feature of the node. And then another piece of notation, we are going to denote n of v to be a set of neighbors of a given node v. And that's basically the notation, the setup we are going to use for this part of the lecture. Now, if you say, how could I go and apply deep neural networks to graphs? Here is a naive, simple approach. The idea you could have is to say, why don't I represent the network with the adjacency matrix, and then why don't I append the node features to the adjacency matrix? Now think of this as a training example and feed it through a deep neural network. Right? It seems very natural. I take my network, represent it as an adjacency matrix, I append node features to it. Now this is, the input to the neural network, and I'm able to make predictions. The issue with this idea is several. First is that the number of parameters of this neural network will be multiple times the number of nodes in the network, because the number of inputs here is the number of nodes plus the number of features. And if you say how many training examples I have one training example per node. So it means you'll have more parameters than you have training examples, and training will be very unstable and it will easily overfit. Another issue with this is that this model won't be applicable to graphs of different sizes, because if now I have a graph that has 7 nodes, it's unclear how to fit a graph of 7 nodes into 5 different inputs. Right? Because here we had a graph of 5 nodes. So that's one big issue. And another big issue is subtle but very important, is that this approach would be sensitive to node ordering. Meaning, right now I number nodes as A, B, C, D, and E in the following order, so my adjacency matrix was like this. But now if I would call, for example, node E we call it A, B, C, D, and E, then the shape of my adjacency matrix would change, right? The nodes would be permuted, rows and columns of the matrix would be permuted, even though the information is still the same. And in that case, the model would get totally confused and wouldn't know what to output. So the point is that in graphs, there is no fixed node ordering, so it's unclear how to sort the nodes of the graph that you could, put them as inputs in the matrix. That's much easier in images, because you say, I'll start with the top left pixel, and then I'll kind of go line by line. In the graph, the same graph can be represented by many different adjacency matrices, because it all depends on the ordering or in which you labeled or numbered the nodes. So we have to be invariant to node ordering. So the idea, what we are going to do is we are going to kind of borrow some intuition from convolutional neural networks, from computer vision, but generalize them to graphs. So here's a quick idea about what convolutional neural networks do, right? If you have an image here, represented as this grid, then you define this convolutional operator, basically this sliding window that you are sliding over the image, right? You start at top left. This is now a 3x3 operator. You compute something over this area of the image, and then you slide the operator by some number of steps to the right and apply the same operator again. And you can keep doing this, and you can imagine that now this will give you a new image of different size, of different different number of rows and columns, to which you can apply another convolutional operator, another kind of sliding window type operator that kind of goes over the rows of that image. And if you chain this together, you can then come up with convolutional neural networks and good predictions. Our goal here is to generalize this notion of convolution between simple lattices, beyond simple matrices, and also leverage node features and attributes, like, for example, text or images that might be attached to the nodes of the network. The issue is that our networks are much more complex. So defining the notion of a sliding window, let's say a 3x3 window, is very strange, because maybe in some case the sliding window may only cover 3 nodes. In other case the sliding window may cover many more nodes, and it's unclear how to define this notion of a window, and then it's also unclear how to define the notion of sliding the window over the graph. And this is a big complexity and a big challenge that graph neural networks have to do to be able to be applied to complex network data. So the idea that makes this work is the following step in intuition. So the idea is that single layer of a convolutional neural network, basically what it does, it, for example, takes the area of 3x3 pixels, applies some transformation to them, and creates a new pixel. And that's the way you can think of it, right? And now we can take this operator and slide it across the image. What we'd like to do in the graph is something similar, but if you want to apply this operator in terms of a let's say like a sliding window, then we will have a center of the sliding window, which is a node, and this center is going to kind of borrow, aggregate information from its neighbors, right? The same way here, you can imagine that this is the center of the operator, and it's kind of collecting information from its neighbors, denoted by arrows, takes its own value as well, and creates a new value, a new pixel for itself. So the idea is that what convolutional operators are really doing, they are transforming information from the neighbors, combining it, and creating a new kind of a message. So this is when today's lecture also relates to the last lecture when we talked about message passing, right? So today here we can think about a node collecting information from its neighbors, collecting messages from its neighbors, aggregating them, combining them, and creating a new message. So that is the idea. So how graph convolutional neural networks are going to work? The idea is that node's neighborhood defines the neural network architecture. So basically the structure of the graph around a node of interest defines the structure of the neural network. So the idea is, if I want to make a prediction for this red node I here in the network, then the way we can think of this is that I is going to take information from its neighbors, and neighbors are going to take information from neighbors of neighbors, and we are going to learn how to propagate this information, how to transform it along the edges of the network, how to aggregate it, and how to create a new message that then the next node up the chain can again aggregate, transform, and compute. So in some sense, the way we can think of graph neural networks is a two-step process. In the first step process, we determine the node computation graph, and in the second process, we then propagate the information, we propagate and transform it over this computation graph. And this computation graph defines the architecture or the structure of the underlying neural network, right? So in this way, we learn how to propagate information across the graph structure to compute node features or node embeddings. So that's the intuition. Let me give you an example what I mean by this. Consider here a very small input graph on 6 nodes. And what we will want to do is, the key idea will be that we want to generate node embeddings based on the local structure of the neighborhood around that target node. So for this input graph, and this is the target node, here is the structure of the neural network that is going to make computation to be able to make a prediction for node A. And let me explain you why is this neural network has this structure. The reason is that node A is going to take information from its neighbors in the network, B, C, and D. So here are B, C, and D. And then, of course, this is kind of one layer of computation, but we can unfold this for multiple layers. So if we unfold this for one more layer, then node D takes information from its neighbor A. And that's why we have this edge here. Node C, for example, takes information from its neighbors, A, B, E, and F. They are here, A, B, and F. And then D takes information from A and C because it's connected to nodes A and C. So now, what does this mean is that if this is the structure of the graph neural network, now what we have to define, what we have to learn, is we have to learn the message transformation operators along the edges, as well as the aggregation operators, right? Because node B says, I will collect the message from A, I will collect the message from C, these messages will be transformed, aggregated together in a single message, and then I'm going to pass it on. So that now node A can again say, I'll take message from B, I will transform it, I will take message from C, transform it, message from D, transform it. Now I'm going to aggregate these 3 messages into the new message and pass it on to whoever is kind of in the layer above me. So that is essentially the idea. And of course, these transformations here, aggregations and transformations, will be learned. They will be parameterized, and this will be the parameters of our model. What is interesting and fundamentally different from classical neural networks is that every node gets to define its own neural network architecture, or every node gets to define its own computation graph based on the structure of the network around it. So what this means is, for example, that blue node D here, its computation graph will be like this, will be very skinny because D takes information from A and A takes it from B and C. So it's this is now a 2-layer neural network, but it's very skinny, very narrow. While, for example, node C has a much bigger, much wider neural network because C collects information from its 4 neighbors, and then each of the neighbors collects it from its own set of neighbors. So the architecture, structure of this green neural network corresponding to target node C is very different than the one from the node D. So what is interesting conceptually is that now every node has its own computational graph or has its own architecture. Some nodes, if the neighborhood of the network around them is similar, for example, these 2 nodes will have the same computation graphs, right? This is E and F. You see that kind of the structure of these computation graphs, this neural network architecture trees is the same. But in principle, every node can have its own computation graph. That's first thing. And then the second thing that's interesting, now we are going to train or learn over multiple architectures simultaneously, right? So it's not that we have one neural network over which we train. Now every node comes with its own neural network architecture, neural network structure. And of course, the structure of the neural network for a given node depends on the structure of the network around this node, because this is how we determine the computation graph. And that's kind of a very important kind of deep insight into how these things are different than kind of classical deep learning. So now, how does this work as we have multiple layers, right? So the point is that the model can be of arbitrary depth. We can create an arbitrary number of layers. And nodes have embeddings at each layer, and the embedding at layer 0 of a given node is simply initialized as its input features x. And then the layer K embedding gets information from nodes that are kind of K hops away, right? So the way this would work is layer 0 embedding for nodes is simply their feature vectors. So here denoted by X. Then, for example, embedding of node B at layer 1 would be some aggregation of feature vectors of neighbors A and C, plus its own feature vector, and this will be now embedding of this node at layer 1. And then this will be passed on so that now node A can compute its embedding at layer 2. So what it means is that the embedding of A at layer 0 is different than its embedding at layer 1. At layer 2. So at every layer, a node will have a different embedding. And also, we are only going to run this for a limited number of steps. We are not going to run this kind of infinitely long or until it converges as we did in the last lecture. We don't have this notion of convergence. We'll only do this for a limited number of steps. Each step corresponds to one layer of the neural network, corresponds to one hop in the underlying network. So if we want to collect information from K hops away from the starting node, from the target node, we are going to need a K layer neural network. And because networks have final diameter, it makes no sense to talk about, 100 layer deep neural networks. Again, unless your network has diameter or the longest, shortest path is of 100 hops. So now that we have defined the notion of how do we create this computation graph based on the structure of the neighborhood around a given node, now we need to talk about these transformations that happen in the neural network. And the key concept is neighborhood aggregation. And the key distinction between different approaches, different graph neural network architectures is how this aggregation is done, how this information from children nodes is aggregated and combined with the information or message of the parent. One important thing to notice is because the ordering of the nodes in a graph is arbitrary, this means that we have to have our aggregation operator to be permutation invariant, right? So it means that we can order the nodes in any order, and if we aggregate them, the aggregation will always be the same, right? That's the idea. It doesn't matter in what order we aggregate. We want the result to be always the same, because it doesn't matter whether node B has neighbors A and C or C and A. It's just a set of elements. So it doesn't matter whether we aggregate in a sense from A and C or C and A. We should always get the same result. So neighborhood aggregation function has to be order invariant or permutation invariant. So now, of course, the question here is that we haven't yet answered is, what is happening in these boxes? What do we put into these boxes? How do we define these transformations? How are they parameterized? How do we learn them? So the basic approach is, for example, is to simply average information from the neighbors and apply a neural network. So a summation is permutation order invariant, because in any number you sum up the numbers, in any way you sum up the numbers, you will always get the same result. So average or a summation is a permutation invariant aggregation function. So for example, the idea here is that every of these operators here will simply take the messages from the children and average them, and then decide to take this average and make a new message out of it. So the way we can do this is we aggregate the messages, and then we apply a neural network, which means we apply some linear transformation followed by a nonlinearity to create a next level message. So let me give you an example. The basic approach is that we want to average messages coming from the children, coming from the neighbors, and apply a neural network to them. So here is how this looks like in equations, and let me explain. So first, right, H is our embedding, and subscript means the node, and superscript denotes the level of the neural network. So at the beginning, at the 0th layer, the embedding of the node V is simply its feature representation. And now we are going to create higher order embeddings of nodes, right? So this is at level 0. So at level 1, what are we going to do is written here in equation, and let me explain. So first we say, let's take the embeddings of the nodes from the previous layer. So this is the embedding of this node V from the previous layer. And let's transform it with some matrix B. Then what we are saying is, let's also go over the neighbors U of our node of interest V, and let's take the previous level embedding of every node U. Let's sum up these embeddings and average them. So this is the total number of neighbors. And then let's transform this aggregated average of embeddings of children, multiply it with another matrix, and send this through a nonlinearity, right? So basically we say, I have my own message, my own embedding, if I'm node V, my own embedding from the previous layer, transform it, I aggregate embeddings from my children, from my neighbors from previous level, I multiply that with a different transformation matrix, I add these two together and send it through a nonlinearity. And this is now one layer of my neural network. And now, of course, I can run this or do this for several times, right? This is now how to go from level L to level L plus 1. To compute the first layer embeddings, I use the embeddings from level 0, which is just the node features. But now I can run this for several kind of iterations, let's say several layers deep, maybe 5, 6, 10. And then whatever is the final hidden representation at the final layer, that is what I call the embedding of the node, right? So we have a total number of capital L layers, and the final embedding of the node is simply h of v at the final level of neighborhood aggregation. And this is what is called a deep encoder, because it is encoding information from the previous layer from a given node plus its neighbors, transforming it using matrices B and W, and then sending it through a nonlinearity to obtain next level representation of the node. And we can basically now do this for several iterations, for several layers. So how do we train the model if every node gets its own computational architecture and every node has its own transformation parameters, basically this W and B? The way we train the model is that we want to define what are the parameters of it. And parameters are these matrices W and B, and they are indexed by L. So for every layer, we have a different W, and for every layer, we have a different B. And the idea here is that we can now feed these embeddings into the loss function, and we can run stochastic gradient descent to train the weight parameters, meaning BL and WL. These are the two parameters, right? One is the weight matrix for neighborhood aggregation, and the other one is the weight matrix for transforming hidden vector embedding of the node itself to create then the next level embedding. So this is how we do this. What is important is that these weight matrices are shared across different nodes. So what this means is that this L and B are not indexed by the node, but all nodes in the network use the same transformation matrices. And this is an important detail. As I have written things out so far, I have written them out in terms of nodes aggregating from neighbors. But as we saw earlier in graphs, many times you can also write things in the matrix form. So let me explain you how to write things in the matrix form, right? Many aggregations can be performed efficiently if you write them out in terms of matrix operations. So what you can do is you can take your matrix H and simply stack the embeddings of the nodes together, like here. So every node is an embedding for a given node at a given layer. So we can define this notion of a matrix H superscript L. And then, right, the way I can simply compute, then basically if I say what is the sum of the embeddings, aggregation of embeddings of nodes U that are neighbors of V, this is simply taking the correct entry in the adjacency matrix and multiplying it with the matrix H. And this way, I'm basically averaging or aggregating the embeddings coming from the neighbors. Then I can also define this notion of a diagonal matrix, where basically this matrix is zero. Only on the diagonal of it, we have non-zero entries that are the degrees of individual nodes. And then if you say, what is the inverse of this diagonal matrix D? It is another diagonal matrix where on the edges, where on the entries on the diagonal, I have now 1 over the degree. So that D times inverse of D is an identity matrix, right? So now, if you take this and combine it with this D minus 1, then you can write the neighborhood aggregation, basically averaging of the neighborhood embeddings, simply as D to the minus 1, so the inverse of D times adjacency matrix times the embeddings at level H, at level L. So basically, what this means is that I can write things in terms of this summation and averaging, or I can write it as a product of 3 matrices, a product of this diagonal matrix that has 1 over the diagonal, 1 over the degree on the diagonal, so this corresponds to this term. A corresponds to summing over the neighbors, and H superscript L are the embeddings of the nodes from the previous layer. So this means I can think of this in terms of this kind of matrix equation, or I can write it basically as neighborhood aggregation. So rewriting the update function in matrix form then is like this, right? It's basically take the your embedding and multiply it with B, take the embeddings of the neighbors from previous layer and multiply them with W. So red part corresponds to neighborhood aggregation, blue part corresponds to self-transformation. In practice, what this implies is that efficient sparse matrix multiplication can be used to train these models very efficiently. So you can basically represent everything as matrices, and then you have matrix gradients, and everything will work very nicely. Now, in the last few minutes, I want to talk about how to train this thing. So the node embeddings Z are a function of the input graph. And we can train this in a supervised setting, in a sense that we want to minimize the loss, the same way as we discussed so far, right? I want to make a prediction based on the embedding, and I want to minimize the discrepancy between the prediction and the truth, where, you know, Y could be, for example, a node label or a scalar value. Or I could even apply this in an unsupervised setting where I would say, I want, you know, the similar, where node labels are unavailable, I can use the graph structure for supervision. So I could define the notion of similarity and say, you know, the dot product between the embeddings of 2 nodes has to correspond to their similarity in the network. And I could use now deep encoder to come up with the embeddings of the nodes rather than using the shallow encoder. But I would use the same decoder as in node2vec, meaning the random walk and similarity matching using the dot product. So that's, I can apply this in both settings. To explain how I could do unsupervised training a bit more, so the idea would be that similar nodes have similar embeddings. So the idea would be that, you know, let y uv denote have value 1 if node u and v are deemed similar. For example, they co-occur in the same random walk as defined in node2vec. Decoder of the 2 embeddings, let's say, is a simple dot product. It says embedding of 1 times the embedding of the other, and we want the discrepancy between the similarity and the similarity in the graph versus similarity in the embedding space to be as small, so we can define this through the cross entropy. And then we could again just basically run this optimization problem to come up with a graph neural network that makes the predictions as we discussed. So the way we are going to train this is that we are going to train this either, as I said, in this kind of unsupervised way, and of course we can also directly train this in a supervised way, which means that perhaps, you know, for a given node we have some label about the node. Maybe this is a drug-drug interaction network, and we know whether this drug is toxic or not, whether it's safe or toxic. So we could then say, you know, given this neural network, predict at the end the label of the node, whether it's safe or toxic. And now we can backpropagate based on the label. So both are possible. Either we directly train to predict the labels, or we can train based on the network similarity, where network similarity can be defined using random walks, the same way as in Node2Vec. So for supervised training, basically what we want to do is we want to define the loss in terms of, let's say, classification. This is the cross entropy loss for a binary classification. Basically, here is the prediction of the label for a given color, whether it's toxic or not. This is whether it is truly toxic or not. And then the way you can think of this is y takes value 1 if it's toxic and 0 if it's not. If the true value is 0, then this term is going to survive, and it's basically 1 minus the log predicted, 1 minus the predicted probability. So here we want this to be the predicted probability to be as small as possible, so that 1 minus it becomes close to 1, because log of 1 is 0, so that this discrepancy is small. And if the class value is 1, then this term is going to survive, because 1 minus 1 is 0, and this goes away. So here we want this term to be as close to 1 as possible, which again would say if it's toxic, we want the probability to be high. If it's not toxic, we want the probability to be low, the predicted probability of it being toxic. And this is the cross entropy loss. So this is the encoded input coming from node embeddings. These are the classification weights for the final classification. And these are the node labels. Is it basically toxic or not? And I can optimize this loss function to basically come up with the parameters b and w that give me the embedding that then makes good or accurate predictions. So let me just give an overview and finish and complete the lecture. So the way we think of model design is that given the graph, we want to compute the embedding of a target node. First, we need to define the neighborhood aggregation function. This is the first thing we have to do. The second thing we have to do then is to define the loss function on the embedding, like the cross entropy loss I was just discussing. And then we need to train. And the way we can train the model is that we train it on a set of nodes on a batch of nodes. So we select a batch of nodes, create their computation graphs, and this is a batch of nodes on which we train. And then what is interesting is that after the model is trained, we can generate embeddings for any nodes as needed and simply apply our model to them by basically just doing the forward pass. So this means that we can apply our model even to nodes that we have never seen during training. So this means that we can train on one graph and transfer the model to the other graph, because this particular set of nodes could be used for training. The parameters would be optimized here, and then we could apply this to a new set of nodes, to a new set of computation graphs. So this means that our model has inductive capability, which means that same aggregation parameters, same W and B, are shared across all nodes. And the number of model parameters in this case is sublinear with the size of the network, because W and B only depend on the embedding dimensionality and the size number of features, and not on the size of the graph. And this means that graph neural networks are able to generalize to unseen nodes. And that's a super cool feature of them, because, for example, this means that you can train your graph neural network on one graph and you can apply it to a new graph, because you determine matrices W and B here, and then you can transfer this to the new network. You can, for example, train on one organism and transfer this to the new organism. This is, let's say, a biological network. This is also very useful for networks that constantly evolve, because you can take the snapshot of the network, create the computation graphs here, and determine the parameters, so that when then in production a new node arrives, you quickly create a computation graph for it, just do the forward pass, and here you have the embedding for it. So no retraining the model is necessary. And that is super cool, because it means you can train on one graph, transfer to another one, train on a small graph, transfer the model to a big graph, or to an evolving graph. So let me summarize the lecture for today and finish here. What we did is we generated node embeddings by aggregating node neighborhood information. we saw a first basic variant of this idea that simply averages up the messages coming from the neighbors. And the key distinction between different architectures, as we are going to see next, is how this aggregation process is being done. And what I'm going to discuss in the next lecture will be the architecture called Graph Sage that generalizes this into basically a framework where different types of aggregations, different kinds of transformations can be used. So thank you very much for the lecture, and very happy to take questions now.